This is video B6. Very importantly, note that this is a calculator problem. Simply don't forget you have a calculator on your desk for this one. Okay, and so you've read it. We have two rates that we're dealing with. Okay, one, a rate at which water is being pumped into a tank, and this rate is in liters per hour over a time period. And the other rate is how quickly water is being removed from the tank, once again in liters per hour. Okay, here we're given the function. Here we're given measurements at given times. Okay, and they tell you that R is both differentiable and decreasing on the entire time. And you can see that the values of R are decreasing, but what this means is that we aren't going way up here and then coming back down, way up, coming back down, and that'll be important for a later answer. Okay, your first problem, estimate the slope of R, the derivative of R, at t equals 2. Okay, note they don't give you information about when t equals 2. But the derivative of R, and R is a function of t, so this would be with respect to t, is simply the slope of this curve. And since we're estimating it, the only information they give us that we really could use for that would be these two ordered pairs here. And so I just used the slope formula. And there I have the two ordered pairs. So y2 minus y1 over x2 minus x1. Okay, note that our slope is negative because r is a decreasing function. And then they say use the correct units, and they would definitely look for that. So you have this rate in liters per hour. You derived it with respect to time. So it's liters per hour. And so that sounds like an acceleration. And in this case, we would have a negative acceleration since the rate is decreasing. All right, part B. A left Riemann sum with all of this information. Okay, and so we're going to use, since it's a left Riemann sum, the leftmost ordered pair in each interval. That would make this ordered pair unnecessary for us. So we're using it to estimate the total amount of water removed. Okay, and so this Riemann sum is going to be, and I'll show you it. Okay, I plotted the points, and the area under each of these rectangles will approximate the area under the curve, and the area under the rate curve will be an amount. In this case, it's going to be liters, because each of these right here, each rectangle has a height measured in units of liters per hour. Okay, and we're multiplying that by a base, which is measured in hours. So we have liters per hour, liters over hour times hours, and we just end up with liters. So note also that I didn't use the rightmost point here. And so I found the area of each rectangle. And then they ask, is this an overestimate or an underestimate? And we did one not too dissimilar to this. Okay, our function is decreasing, and so it might look something like this. And note, with this decreasing function, the left Riemann sum gave us rectangles in each interval that are too big. And so the rectangles, the Riemann sum, would be an overestimate. Part C. So we're going to use that answer to estimate the total amount of water in the tank after the 8-hour period. And so what we need to find now is the total amount of water will be the water that came in minus the water that was removed plus the water that was already there. And they gave you information earlier about that. We started with 50,000 liters of water. Okay, well, remember, this is our answer from part B. So the water removed was that many liters. Okay, here's our water already there. Here we have the area under the other rate curve, the rate curve with the water coming in. And this would be a very difficult, time-consuming integral, and they don't want you to do that. So this is where you have to remember that you have a calculator. Honestly, if you are on a problem and you think, well, that's going to take way too long, just ask yourself, can I do this on a calculator if you have it? And you do get a calculator on this year's AP test. All right, and so I just used the calculator and I evaluated it and I included my units again. All right, last one. Is there a time when the rate at which the water is pumped into the tank is the same as the rate at which water is removed from the tank? I think this is the kind of problem that they may be asking you this year. Okay, so be alert for an intermediate value theorem problem. Okay, so they're asking this. The water in, is it ever equal to the water going out? These two rates. So I'm trying to solve this, and I don't have enough information to find it because I don't know all the values of R of t. But what I do know is this. If I subtract it, then I get another problem. So I have a new function here, and I'm being asked from 0 to 8, is it ever equal to 0? Okay, and this would be a continuous function in 0 to 8, and since R is differentiable, it would also be continuous from 0 to 8. And so this is a continuous function. So what they're really asking is there a negative value of this function somewhere on this interval? And then is there a positive value of this function somewhere on that interval? Because if there is, and this is continuous, then the function would have to go through 0 at some point on the interval. And so we do have information about these values. We can evaluate those values. Okay, this is definitely calculator work, not that actually. But note that here I do get a positive value for this function. Here I get a negative value. And then and they would want you to show that you understand that you have to have a continuous function in order to be able to use the intermediate value theorem. So you would state that since this is continuous on that interval, and since we have a positive and a negative value, there must be some value on which the function equals 0, which would mean that the rates would be equal at that time. All right, so tomorrow's question, once again, a no calculator